All right, here it is. It's the moment you've all been waiting for. I know you've just been so excited to get to this unit. You've been like, oh yes, all I want to do is I want to write my own functions. I'm so tired of using other people's functions, I'm going to write my own. I know that's what you've been doing at home, and it is here. We are now going to learn how to write our own functions in R. So why would you want to do this? Why do you even bother? Well, the basic idea is that writing functions allows you to automate certain common tasks. Really, that's what's happening with the functions that you already have, right? You've already been using the built-in functions in R to automate certain processes. You might find that in your life, you have some processes that are kind of specific to your analysis, and you find yourself doing them over and over. So for example, so far in this class, have you found yourself frequently copy-pasting your old code and changing bits of it? I bet you did that in the lab, the hip-hop lab, because in that lab, I asked you to do a very similar analysis, where you were finding the most familiar and unfamiliar words. But I asked you to do it a few repeated times, where you were using different demographics. I'm guessing what you did is you completed the first task, you copy-pasted everything, and then you changed the parts that you needed to change to make it relevant to the second question being asked. And that's great. There is nothing bad about that. You should absolutely copy-paste your code. You should absolutely reference your own work. This is good. But if you find yourself doing this too frequently for the same task, it might be useful to have just one function that does that for you. So writing your own function has basically three big advantages over this copy-paste process. The first one is that it really does streamline your code. It makes it so that if I look through your analysis, it's pretty easy to see what you're trying to do. That is, if you've given your function a reasonable name that describes what it's trying to do. And so instead of seeing every little detail of the process every single time you do it, I'm just seeing, okay, this is the part where we found the most familiar words for that particular demographic. Another advantage here is that if the task changes, if suddenly something comes up and you decide, ooh, I really want to tweak my analysis a little bit. If you've written a function, all you have to do is tweak that function. You don't have to go find every single spot where you've copy-pasted and make the relevant edits. You just have to edit it once. And lastly, it does get around these common mistakes from copy-paste. We saw that in the last lecture when we were duplicating a process, and it was very easy to miss one bit, not change the element that you needed to change, and then it doesn't give an error, but it's not doing exactly what you hoped. So if you have a function, then you aren't going to make that kind of mistake. So here's a very simple function. It's very exciting. Try to calm yourself here. I know this is some really whiz kid programming here. What this function does is it takes a number and it adds 2. Oh my god. Oh, best function ever. But anyway, this function did not exist before I wrote it into R. I wrote it, and what I did is I said, give me a number, and what I'll do is I will add 2 to that number. And so this part of the code is the part where the function is being defined. In this part of the code, we're using that assignment operator that we typically use to make objects. And that's all that we're doing here. We're making a new object. That object is called add2, and it happens to be an object of the type function, rather than like a data frame or a vector. And so once we've run this part of the code where we defined that object, now it exists, now that function has been taught to R, and now we can say, please add 2 to 5 and get back the result. Fortunately, math still works, my computer isn't broken, we get back 7. And so in this case, that x is not really meaningful. I've had a few x's that weren't very meaningful. But in this one, that x is just a placeholder, right? So we're saying, look, you give me something, and whatever that something is, I'll add 2 for you. And so when I run the function, when I call it, I say, here's a 5, and then that 5 gets sent along under the name x. It goes here, it gets 2 added to it. Now that name of the function is the first thing you're going to have to choose when you write a function. The name is chosen by the author. Every function you've used so far, the existing ones, they were chosen by whoever wrote it. Here I've chosen the name add2. Good job me, I've chosen an informative name. I've chosen one that tells the user what they should expect. But of course, I didn't have to, right? I just chose that name. So function names don't have any meaning in and of themselves. I have just named my object. I could have named it Gilbert. Instead, I named it add2. So here's a function that I've named add3. And if I just showed you this part of the code, you would expect an output of 8, right? You would expect if I add 3 to 5, I get 8. But add 3, it's just the name of the function. It doesn't necessarily guarantee what's happening. And you can see that this function I've written actually adds 7. So when you are writing your own functions, choose a name that is specific, that implies what the function is doing, that when you go back later and see it and you guess what it's doing, you will be correct. And also don't necessarily trust that other people's functions do exactly what you think they should do. The next thing you have to decide when you're writing a function is what will be the arguments. So in this original example of add 2, I chose to have one argument and I named it x, and here's what I did with that argument when I got it from a user. And then the last anatomy of the function is the body. The body is what we refer to as all the code that's inside these two curly brackets. And this is where the action happens, right? This is where we say, okay, I've given you my arguments. What the heck do you want me to do with them? This is where you write ordinary R code, except that it's happening wrapped inside this beautiful function. So let's talk a little more about arguments, because I think choosing carefully your arguments and understanding how they get sent along to the body is the most central point with writing functions. So the first thing I want to say is that you should not ever rely on the outside world inside the body of your function. Once you get really, really experienced with this, if you've written a lot of functions, then there's some shortcuts. I have been known to cheat with this. But I'm going to tell you for this class, never do it. Never reference an object that hasn't been passed along as part of the arguments to your function. So here's an example. I have altered add 2. It looks the same in the body where I add 2 to x, but now I don't have an argument named x. Now I just have a blank no function or no argument function. So if I try to run it for the first time, it's going to say, ugh, I can't find x. What are you doing? You didn't give me anything in this function to define x. But then, outside of the function, independent of anything happening in the body of the function, I've made a variable called x. And what this function does is when it can't find x being passed as an argument, it's a little too smart for its own good. It's going to zoom out and look outside of that function. And in this case, because I've made something called x, it will find it and get back 12. This is bad. This is not reproducible. We can see here, I ran the exact same line of code twice and got different results. That shouldn't happen. I should run the same line of code and get predictable results. It's also missing some information. If I looked at this add 2 and saw the output, I wouldn't necessarily know exactly what it was adding to. Now the next thing you need to decide is if there are any optional arguments. So there are the things that someone has to give your function for it to work. It can't do its job unless it has something to add 2 to. But let's suppose instead of adding 2, I want it to be more general. I want to write a function that adds something to your original number x. But what I'd like to do is not be too strict. If the user doesn't want to choose, I'm going to choose for them, and I'm going to choose 2. So here I've said the first argument, I've named it x. The second argument, I've named it something. And I've set this default value of 2. Because in my function definition here, I have chosen a default value, that means that the user doesn't have to use that argument. So if I run this function, add something, on the number 5, I'm still adding 2. That was the default. But I do, as a user, have the option to specify when I run the function, actually I wanted to add 6, and then that will work too. If you do not do this, if you don't give a default value in the function definition, that argument is required. So we just saw this a second ago here. If I try to run add something and I don't give it x, when I define this function, have not supplied a default value for x. So instead of inserting some default, it's going to break. It's going to say, look, buddy, you tried to run me, but you didn't give me my argument. What the heck am I supposed to do? So you'll get an error. So as you're writing your function, you have to think about when you want those errors to happen. You want this function to break if a user doesn't give you appropriate information. But maybe there's some information that is nice to have the option, but you don't need the whole function to break if it's not there. So once you've decided on the function and you've decided what goes into the black box, you need to think about what comes out of that black box. So basically, the way to think about it is in that body of the function, if it were not inside of a function, what would print out? If you just ran this in your console in R, what would print out? That's basically what the function is giving back. And so here, if I run this in console, 7 plus 2, it's an atomic vector containing one element, which is 9. And if I run the function, that's also what I get back. Now you can be a little more explicit by using this return statement. There's some disagreement about this return statement. Personally, I really prefer to always have it because I like being able to look at a function definition and know what is the final product being handed back. Some people think that it's overkill, think that for a function that's simple like this, where we're just returning x plus 2, it's rather silly to wrap that up in the return function. It's very clear in this previous slide what's being returned. So it's up to you. You don't have to use this return statement. You can instead just rely on whatever the final product is getting returned. But I'm going to recommend it, and for this class, because I'm grading you, it'll make my life easier if you make it really clear in your functions, what are you handing back? Now with these returns, what you do to the function does not change the state of, I'm going to call real life, the state of the world outside of the function. So here's an example. What I've decided to do is kind of split my add2 into 2 steps. In the body of this function, I have made an object called myResult, and I've chosen to return that object out of the black box. And now outside of the function, now I've already defined this function, I move on with my life, I make something called myResult with the value 2000. And then I run this function add something. And you might think that because this line of code is kind of under the hood getting run when I call my function, that it's going to change that object myResult. But in fact, it doesn't. In fact, if I look at my result, that's still 2000. What happened inside the function, regardless of how things are named, is not going to influence the world outside the function. Now, I will say, like most things in R, there is a way to cheat with this. You are not allowed to use it right now. Pretty much no one is allowed to use it. One day, maybe if you take advanced R, you'll learn it. But don't do this. If you stumble across it, don't do it. What happens in your function, it's like Las Vegas. It stays in your function. And I'll just take a moment to clarify this vocab word. The reason for that is that in R we think of environments. And this word might sound familiar because in the top right pane of your RStudio window, you see your environment. You've probably gotten in the habit now of checking it to kind of see which objects have been defined and what they contain. That environment is what's called your global environment. That's the one that you're currently working with in your RStudio pane. When you do a function, the stuff that happens under the hood in the body inside the black box, it happens in its own baby environment. We call it the function environment. It doesn't do anything to your global environment. And so in fact, this is what's going on when you knit. You remember how if you knit, it doesn't really matter what you've done in your home base RStudio. It only matters what code actually exists in that R Markdown document. And that's because when you knit, R zooms out into a whole new, fresh environment, and that's where it runs through your code. So we can have many environments happening. They're kind of like little pocket universes. What's relevant to today is that the function environment is separate. It doesn't do anything to your global environment. Now with this return statement, you might want to return different results depending on what you get. So what comes into the black box determines what comes out of the black box. And this is where I think these return statements are really helpful for clarifying what's happening when. So here's an example. This is a function that decides if a number is even or odd. So I give it some number x. It says, hey, if I divide x by 2 and look at the remainder, is that equal to 0? If it is, then we'll return even. If not, we skip this part and move on to return, hey, it's odd. So we can see here the green and the pink. These are 2 different possible returns within the same function. I also want you to be careful with the idea of printing versus returning. Basically, a function is a black box, right? Something comes in, something comes out. We want to think about those objects and what type they are. But it's also true that that function, that black box, can make some noise. That black box can spit some stuff out, can shout at you while it's doing its work, and then just return an unrelated object. And so in this first example, this even or odd example, we are literally returning an object which is a string. if I were to take this function and run it and store the output in an object named Bob, that object Bob is an atomic character vector. It is a single string announcing whether or not the number is odd. But what I could have done is I could have printed instead, and I'm actually using cat, which is kind of like a nicer formatted print. It behaves the same as the function that's called print. And so here, what I'm doing is I'm not returning these strings. What I'm returning is x. But as my function runs, I have told it to spit some stuff out of the box. I have told it to print out some information. In this case, it's announcing whether this number is even or odd. So if I run this function and I store it under Bob, even though I'm storing it, there is still a side effect. And that side effect is that my function has shouted, hello, it's odd. But that's not what gets stored. If I look at that object Bob, what is stored in Bob is my original number, is 7. Because that's what I passed to this function, and that's what I chose to return, was exactly that same number. So be careful with this. There are situations where you want your function to have side effects. That doesn't mean that those things are what's actually being passed along as the return object. So keep careful track of what's being printed or what's being generated versus what's being returned to the user. All right, so let's try some of this. I would like for you to write a function called times 7. I would like it to take a single argument and multiply that argument by 7. Hopefully this won't take you too long, but I want you to practice writing that function structure. Take a moment and do that now. Okay, hopefully you tried that out and your function works and it's lovely and it really does multiply by 7. It's not a trick function. Now I want a sneak preview on something. Try your function. Try running these two things. Let's make this silly little vector of 7, 8, 9. What happens if you give that vector to your function? It's not quite what you wish would happen, I think. Or what if you give times 7 the data set empty cars? What does it mean to multiply a data set by 7? For this first problem, if you try it out, that's something we're going to hit in the next lecture. The second one I'll address right now. If I try to multiply a data frame by 7, that shouldn't make sense. I want my function to give an error. I want you to remember that errors are not necessarily bad. We would like our code to give us an error rather than to run something that doesn't make sense and get a secret result that is wrong. So here's how you include an error message in your function that you are defining. So here's back to my add something function. And you know what? It's really important that you give me a number. I cannot add a number and a word. I need both of these inputs to be numeric. So I've said, well, let's start by checking to see if that argument something is really a number. And if it's not, the exclamation point here says reverse. If it's true, switch it to false. If it's false, switch it to true. If that happens, we are going to throw an error message. That's what this stop means right here. And the error message is going to say to the user, please enter a number. So here's what that error looks like. Here I tried to add the word Bob to the number 5. Of course, that doesn't make sense. And because I've written the function to look for this error, to check and make sure that that something argument is in fact a number, then I'm getting back an error. R will automatically tell you which function the error occurred in. And here's the message that we decided we wanted our function to give to the user. Please enter a number. So now let's take your times 7. Let's try out some of those extra things, the side effects with printing and the error messages. Alter your times 7 function such that it still takes the argument and multiplies by 7, but it makes sure that that argument is in fact a number. And also, I want it, if the argument is itself a 7, I want your function to get excited and shout out, I love 7s. I don't want it to return the string I love 7s. I want that to be a side effect. Try that now. Okay, so hopefully you were able to use the stop function, the cat function, the return function, and also some nice if statements to make this happen with your times 7 function. Now remember the sneak preview. Try these things again. Make that weird little vector 7, 8, 9 and see what happens when you give it to your function. It's not quite what you'd hope. Now we know how to write a function, or at least a simple one. When should this happen? When is a good time to pause what you're doing and take some time to actually construct a function? Well, there's kind of a rule of thumb which says 3 or more times is too many. If you have copied and pasted the same code more than twice, you should probably instead write yourself a function to do that code. So here's an example. Here's some rather gnarly code. I've made a new data frame called myIris, and I'm just storing this iris data. It's built into R. You can check it out if you want. And now here's 4 lines of rather repetitive code that I want you to take a look at and tell me what it does. So what this is doing is it's trying to standardize each of these 4 variables. These variables are measurements on a flower, and we're trying to subtract the mean and divide by the standard deviation. So it's standardizing the variables to be centered at 0 and have a standard deviation of 1. Does it actually do that? Does it do what you wanted? Probably you looked at the first line, figured out what was going on, maybe it took you a little bit, and then you said, okay, that's been duplicated 3 more times, and that was reasonable. Check it out. Here's what happened. In that first line of code, we indeed used sepal length. We took sepal length, we found its mean, we found its standard deviation, we subtracted and divided appropriately. In that second line, we had copy-pasted the first line and changed everything to sepal width. Makes sense. But we failed. We missed one. We did not change this guy to sepal width. And of course, this is not going to give you an error, right? We really can find the mean of the sepal length, and we really can subtract that from the sepal width. None of those things are not allowed. And so nothing about this code is going to show you that it messed up. It's just going to give you back an updated data set that has numbers that look right but are not correct. This is horrible in data science. This is the #1 thing we want to avoid. These secret mistakes that are hidden, that are hard to find, and they don't throw an error. So let's try to make that process a function. So remember, there's a few things you have to do. First, you have to pick a name. Usually we try to go for verbs. The verb kind of describes the action that the function is doing. And then we need to decide what arguments that function is going to take. And then we have to take that code that we duplicated and instead put it in the body of the function. So here's an example. I've made a function called standardize. That's pretty descriptive, right? And it's going to take in some data. It's going to find the mean and the standard deviation of that data. And then it's going to subtract the mean and divide by the standard deviation. And now here I haven't put a return statement, so it's just going to return the results of that calculation. If I wanted to be a little more deliberate, and this is my personal preference, even though it's more lines of code, I'm going to make a new object called new data that is the standardized version, and that's what I'm handing back, is that updated data. And so I just want to keep reminding you, what object does this function expect, and what does it return? In this case, it's not expecting a data set. It's not expecting a data frame. It's expecting a vector, a numeric vector that it can take the mean and standard deviation of and update accordingly. And so if we wanted to use this function, we would need to give it a vector. We would need to give it that sepal length vector from the dataset iris, not just the dataset myIris. Now these functions can get kind of complex kind of quickly, right? If you're trying to wrap up something repetitive, maybe there's a lot going on there. And so it's often a good idea to write more code that is clearer to read. There's kind of a common misconception in coding that shorter code is better. Absolutely not, and especially not in R, and especially not in data science. The best code is the clearest, easiest to read code. And so in this example, I've said, that was kind of a long line of code where I subtracted the mean and divided by the standard deviation. And there were a lot of parentheses, and it was a little hard to tell where one ended and the other one started. So I've decided, let's do this in 2 steps. Let's make something called deviations, that is, all of the observations minus the overall mean. And then let's take those deviations and divide by the standard deviation of the data. And that's my final object. Let's take a little bit of a break here, not a real break, a break from that process, and say, a thing... All right, so let's pause here. We're going to keep working on this function. But first I want to point out something very important. A big mistake that coders make, especially new coders, is to write a very complex function, run it, it doesn't work, and oh my gosh, now you have to go look through all of this code. It's really important to test what you're doing as you go. To spot check at every step of the process to make sure that step really did do exactly what you wanted. I wonder if in some of the puzzle activities so far, you've run into this problem. You've maybe tried to write the code to address every step and ran it all together and not understood why you didn't get the right answer. Much better to check in and make sure that your steps in your function do what you want them to do. So let's ask ourselves with this function so far. What if we're using a data set that isn't as clean as Iris? The reason people use that one a lot is that it's very nicely formatted, nicely clean data. How about this example? Here's some test data. Here's a vector, and it's a numeric vector, as we'd hope. And when I try to run my standardized function on it, what I get back is a bunch of missing values, a bunch of NAs. Why? Well, hopefully you spotted it has something to do with the fact that my original data had a missing value. And so this is an example of how, if you need to change your process, you only have to change it in one place if you are writing a function. So here I've noticed, the mean function has an argument, an optional argument called na.rm. And this tells the function how to handle missing data, how to handle NAs. Do we want them to break everything, or do we want to just ignore them and drop them? And so here, instead of just subtracting the mean, I've also told it to ignore missing data. And now that I made that change in the body of my function and I rerun this code to redefine the function, now I can put in that new data with the missing value and I get back something reasonable. I get back the standardized data, and of course the missing value is still missing. Compare that to what you would have had to do if you had noticed this problem in your data set in our original duplicated code. Look how many times you would have had to insert na.rm equals true. It's a pain in the butt. Making this slide for you, I hated making it. This is not something you want to have to do in the course of your data analysis. Every time you find something to change, you have to change it a whole bunch of different times.